Hello students. So today we are going to start with Kani's method. Okay, it's one step ahead of moment distribution method. So Kani's method. So Gaspar Kani. He was a German engineer. Okay, so he developed this another distribution procedure, and this method is based on slope deflection equations. Okay, slope deflection, it is based on slope deflection equation. So it's Kani's method, and it is based on slope deflection equation. It is based on slope deflection equation. And you know what is that making it best than other method. So this is the method which is very useful for the analysis of multi-story frame. Okay, so Kani's method, it is useful for the analysis of multi-story frame. And the greatest advantage of this method is, even if we mistake, okay, if we commit any mistake in distribution, if in one of the cycles, okay, if any mistake is happening with us while doing the calculation, there can be some human error, right? So if some mistake is happening during the distribution in one of the cycle, it finally, it can get corrected at the final till we reach the final step. So in spite of that mistake also, we get the correct answer at the end. So even today, many practicing engineers who are not familiar with computer methods, okay, so many of the people, they don't know how to use the computer method, so they still go with the Kani's method, and this is good for the 3 to 4 story building frame. Okay, 3 to 4 story. So people are still using this method. Building BLDG building frame. So let's see how we are going to, let's see the concept behind this particular Kani's method. So here we are going to use some sign conventions. Okay, so sign conventions like clockwise is positive, and if it is anti-clockwise, okay, clockwise rotations are positive and clockwise end moments are positive. So that is means other direction is becomes negative automatically. So let's see analysis of structures without relative displacements at the ends. So let's see this. If we consider any member, okay, let's consider this member, and this particular member, it is having one end a hinge support and other end is also having a hinge support. So we are considering that a member AB. Now this particular member AB, it is something, it is an intermediate member of a beam or a frame. Okay, so some out of from some structure. Okay, so from some structure we have taken some part and we have drawn it here. Okay, so it has no relative displacement at the ends. So ends A and B, they are at same level. So that's what our assumptions are. Now let M of AB and M of BA be the final end moments. Okay, let M of AB and M of BA. Till now we used to calculate this, right, for slope deflection method, moment distribution method. So here also we are considering that M of AB and BA, they are the final end moment. Okay, now M of AB may consist of, okay, it may consist, now if you just see one part of it, okay, one end moment, so it can consist of, number one, fixed end moment, definitely, right? When we write the equation, we know these terms were used to be there. So fixed end moments. Now for this particular case, if we consider it as a figure B. Okay, so let me just draw this diagram first. For this AB, for the AB, if we see this particular diagram here, it can have a rotation like this. It can have a rotation like this. And if we draw tangents over here, it will be like this. So a slope theta A we can show like this, and the slope theta B like this, to the moment M of BA and M of AB, and this is having length L. Okay, total length, overall length is L. the length L. Now let us consider, okay, so this is a typical member. This particular diagram, it is a typical member we have considered. Now let us consider next diagram to show the fixed end moment. Okay, now for this only, the part 2 of this is, let us consider the fixed end moment. So fixed end moments, how we are going to consider that, we will show these are the fixed end. Okay, at the same place we show as a fixed end. So when we want to calculate fixed end moments, our diagram becomes like this. Okay, so this is f of AB, f of BA, and then this is the fixed end moment. Okay, and then moment due to rotation of end A. Okay, so this is the second case is because of the fixed end moments. And then C is because of the moment due to rotation of end A. Okay, if there is a rotation of end A, then how it will look like. So let me just draw this diagram. So again we'll show it as a fixed end. This is also as a fixed end. And we want to show the rotation, so a curve will be like this. Here you can see that because of fixed end, this is, there is zero slope here, but here we are showing the rotation. Okay, so slope will be there to show the slope only, but here there is zero rotation. So because of that, the new moment is m dash AB, and here it is 2m dash AB. That is nothing but 4EI by L. Okay, so we used to use the direct formula 2 theta A plus theta B, right? The same thing we are writing here in a diagram format. Now the last figure, when there is a rotation for end B, okay, when end B is rotating, so in that case our diagram will be B end is rotating. Okay, so for this our diagram will become like this. Okay, so here we can write moment as 2m dash BA, which becomes 4EI theta B by L. So that is 2 theta B, right? We if you remember slope deflection method, this is m dash of BA. So this is moment due to rotation of end B, and here rotation of end A, moment due to rotation of end A, and this is fixed end moment. So these are the 4 conditions, right? So 4 standard conditions, anyway we are aware of it already. So when you consider this case, when you consider case B, so in this case fixed end moment, there is no theta, right? Theta is 0, so theta A is equal to theta B is equal to 0 for this particular case. Now let's see. So we know that let the moment developed at A, okay, let the moment developed at A due to rotation theta A, we know that it is 2m dash AB. So naturally it is equal to 4EI theta A by L. So we are anyways aware of it. So moment developed at B is m dash of AB. Okay. Similarly, when we see B is rotating, so in that case 4EI moment developed is 4EI theta B by L, and it will be half of it at the other end. Okay. So we know the formula with this. Our formula becomes total moment. Okay, total moment m of AB is equal to, first we write the fixed end moment mf of AB plus 2m dash AB plus m dash of BA. So this is nothing but, if you remember our slope deflection equations, mf of AB plus 2EI by L theta A 2 theta A plus theta B, right? The same equation it is. And this is m of BA, here mf of BA plus m dash of AB plus 2m dash of BA. So the moments, this in dash terms, m dash of AB, m dash of BA, they are called as rotation contribution. So they contribute in rotation. So we can also say them as final moment is equal to fixed end moment plus 2 times rotation contribution of near end plus rotation contribution of far end, right? So this is for this near end and then the far end. So when we consider this as AB and we want to write about this, okay, so this becomes near end and this becomes the far end. So that is the formulation. We have used it many times. Now let us consider a typical frame. So suppose this is the frame over here. So I am drawing a typical frame. So this is a frame and then there are okay, consider this as a straight line only. So this is a frame like this. Okay. So in this case, let us name A, E, T, then B and C. Okay. So these are the few points we are considering in this typical frame. Okay. So here consider the moments at A. Okay. Let us consider the moments at A in this particular frame. So we can write, as per above equations. When we can write few moment equation, that is m of AB. Okay. M of AB, m of AC, m of AD, m of AE. So we can write the equations as m of AB. So how we will write equation? That is mf of AB plus 2m dash of AB plus m dash of BA. Then there is other equation mf of AC. So similar way we can write, that is mf of AC plus 2m dash of AC plus m dash of CA. Okay. Similarly we can write that m of AD is equal to mf of AD plus 2 m dash of AD plus m dash of DA. Okay. Then there is m of AE is equal to mf of AE, that is fixed end moment first, and then the moment due to rotation m dash of AE plus m dash of EA. Okay, so this is all, these are the far end, near end, and these are the far ends. Now here summation, if we write summation m of AB, okay, where m of AB is a sum of near end moments in all the members meeting at joint A. Okay, so summation of AB is sum of near end moments in all the members meeting at joint A. Similarly, summation of m dash of F of AB is a sum of fixed end moments in all the members at joint A, and then m dash of AB, m dash of AB. Okay, so whenever dash is there, that is because of rotation. Okay, so sum of near end rotations, rotation contributions of all the members meeting at joint A, and then if we write summation m dash of BA, that is sum of far end rotations contributions of all the members meeting at joint A. So this is the terminology we are going to use. So from the joint equilibrium, okay, if we see the joint equilibrium, we can write that summation of moment AB is equal to 0. Okay, summation of forces AB is equal to 0. Therefore, if we write summation moment F of AB is equal to, okay, summation M. So we can write, in the summation format, we can write the similar equation. So fixed end moment first we'll consider, then we'll consider the rotation effect. So summation m dash of AB plus summation m dash of BA is equal to 0. Okay. So same equation we can write that summation m dash of AB is equal to, just take all the other terms at other side of the equation, half of summation m f of AB plus summation M dash of BA. Okay, so what we are done here, it's very simple. Okay, don't get confused at all. It's nothing but we know that this equations is just this is because of rotation, this is near end and this is the far end. Okay, so we have written equation for AE, AB, AD, AC. Okay, all equations we have written, and then we want to write the summation format, the same equation. So when we say summation of M of AB, so we can write this equation. So we can again rewrite this equation in this format. Okay, so we have basically shown this, that okay, summation M dash of AB is equal to, when all this term go this side and this 2 will become, 2 will go, when it goes to the other side it will become half, right, and the sign will change. So we get this equation. So similarly, for each member which is meeting at joint A, we can write similar equations. So for each member meeting at joint A, so we can write that 2 M dash AB is equal to 4 EI by L theta A is equal to, so 4 EI by L. Okay, so this particular term we can show it as KAB theta A. We can show it as KAB theta A, or we can also write that M dash of AB is equal to half of KAB theta A. So summation term we can write it as M dash of AB is equal to half of summation of K of AB theta A. So similarly again furthermore arrangement of terms. So theta A, let's bring it in front. So summation of K of AB. Now since this theta A is same for all the members meeting at joint A, right? Theta is same for all the members. If you see this diagram, the theta A will be same for all the members. Okay, so in this case we can write that since theta A is small, is same for all the members meeting at joint A, so we can write that M dash of AB divided by summation of M dash of AB is equal to K of AB divided by K of AB, summation of K of AB. Okay, so we can rewrite this equation. So same equation we can arrange the terms and we get that M dash of AB is equal to K of AB divided by summation of K of AB into summation of M dash of AB. Okay, so the last equation what we got, summation of M dash of M, we got this equation, right? Summation M dash of AB is equal to this. So let us call this equation as A, and the recent equation what we got, M dash of AB, let us call it as equation number of B. So let us substitute equation A in equation B. Okay, so the previous equation we are going to substitute it here. So we get the final equation as M dash of AB is equal to minus 1 by 2 K of AB and summation of K of AB, and then substitute summation of M dash of AB. So it's nothing but summation of M of AB plus summation of M dash of AB. Okay, so in this expression half of K of AB by summation of K of AB is called as rotation factor. Important term, it is called as rotation factor for member AB at joint A. Okay, and from this equation Kani developed the rotation contribution method. Okay, so from this equation only we develop rotation contribution method. Rotation contribution method. So at any given problem, okay, at any given problem, the fixed end moments at all the joints can be found. Hence, at any joint, this summation of f of AB, okay, summation of mf of AB, where we have written summation of mf of AB, it can be found. So to calculate the rotation contribution, so if we see this particular equation, the last equation, okay, if we see this equation, so to calculate the rotation contribution, this equation, particular equation, we require the far end contributions. So which we are not doing actually. So we assume them as 0 and we require the, we calculate the near end contribution using this particular equation. Okay. So like this we calculate the near end rotation contributions for the next joint taking the far end contribution. So anyways, when we'll do the practically, when we'll solve the question, then it will become more clear. Okay, so when we actually practically we will do this cycle every step, so that will be more clear. But I think how did we arrive till this formula? I hope it is clear to you till this point. So this is the Kani's method and the concept how it is developed, how we have arrived till this equation. So a very simple method. So students, hope you have understood this concept, and we are going to solve questions based on this in next class. So thank you for listening. Thank you.